to have Sue here, who's visiting us from the IIS at Harvard. And he'll tell us about universal low temperature T-linear resistivity.
Okay.
International quantum critical metals from spatially random interactions.
Okay, thank you very much, Scott, and thank you for the invitation to come to this conference. It's really enjoying my time here at IIS and at Princeton and PCTS. So yes, I apologize for the very condensed matter sounding title. This is based on work done fairly recently with my former student Avishkar Patel, who's at Berkeley, Hayu Guo, who's a current student at Harvard, and Ilya Estelis, who's a postdoc at Harvard. So we've been addressing, some long-standing problems in condensed matter, and I'm excited about our recent progress. But hopefully you'll see that a lot of the progress is inspired by many of the things many of you are working on. Although the problem does have in the end, a condensed matter flavor, and any holographic dual is still an open question for the precise problem that I'll talk about. Okay, so the main problem I want to address is, been around for 20, 30 years. I just show you two recent data plots. So this is the resistivity of lanthanum, strontium, copper oxide as a function of temperature. And what you see is that it's linear in temperature for a very wide temperature range. This is the superconducting critical point, and so that goes superconducting around 40 Kelvin. If you apply a magnetic field, you can even extend this down all the way to low temperature. So now there are many mechanisms for linear resistivity at very high temperatures, from electron phonon scattering or even very strongly interacting electron systems. So that's relatively well understood. But really the mystery is that it goes down to very low temperatures and seems to in principle even go down all the way to 0 temperatures. So the main puzzle, I would say, the challenge is to come up with a model, and at some point it'd be satisfied by any model of some generic interacting quantum many-body system whose resistivity is linear in temperature as temperature goes to 0. And the list of models that do that is very short, and I'm going to tell you the latest candidate today. Okay. So also this behavior is quite ubiquitous. It was first detected in the cuprate superconductors, but it's seen in many other compounds, like the iron-based superconductors, and also more recently in twisted bilayer graphene. Here, of course, the energy scales are much lower, but correspondingly, there's a wide regime of linear T resistivity, typically also at the same point where you get the highest critical temperatures for superconductivity. So, so any explanation should be kind of generic. It shouldn't be specifically focused on your favorite band structure or some kind of singularity in the band structure in a particular compound. It has to be, you would think, rather generic. Okay. So that's the puzzle that's been around, and I'll give you my thoughts, at least our thoughts, I should say, on this problem today. All right. So the basic problem, which many people believe, basic ingredients that should go into any theory, is the following. So of course you have a metal, and metals have a Fermi surface with some occupied states and empty states. So let's just describe it with some dispersion. And the Fermi surface is a locus of points where epsilon k goes to 0. So this is a large momentum. And there's a scale here, which is the Fermi wave vector. So I can't quite think of this as a continuum quantum field theory. But hopefully in the end, we come up with a description where there's some continuum understanding. Okay, so if you now couple this, have the electrons interact, this basic structure is amazingly stable. Almost anything will not only will keep the Fermi surface stable, but also keep long-lived quasi-particles near the Fermi surface. Now, there is a way to destroy the quasi-particle, but not the Fermi surface. And that's to couple the system to some gapless boson in 2 spatial dimensions. So this you can take the boson itself, you can take a continuum limit, so you just have the gradient, some kind of gradient phi squared term. And this boson could be many different things. Could be some kind of symmetry breaking structural order parameter called a pneumatic order parameter, could be ferromagnetism, as long as it's at long wavelengths. Anti-ferromagnetism case is slightly different. Won't talk about it today. Or it could be component of a gauge field. Of course, then there's some gauge invariance to worry about, but it turns out that doesn't matter much at all. The theory is essentially the same. You only need to worry about a certain component and work in a fixed gauge, and the theory becomes exactly the same. Okay, so in principle, you could also use a similar theory for the quark-gluon plasma. So if you take your favorite Yang-Mills theory with massless quarks and you turn on a chemical potential, then in principle, in 2 dimensions, you'll get the theory I'm going to describe. There's a 3-dimensional variant of it, which has also been studied, and it's less singular, but the methods I've described also apply to the physical quark-gluon plasma. Okay, so what's known about this problem of a Fermi surface coupled to a critical boson? So one very important result, which goes back to Patrick Lee's work in 1989, can be obtained by kind of generic perturbation theory. So you have the self-energy of the boson, which is a fermion loop. So you compute this fermion loop, and this gives you a Landau damping term to the boson propagator. And then you take the new boson propagator and perturbatively compute the self-energy of the electron. And when you do this, you get this famous result. So this was the bare electron dispersion. And then you get here omega to the power 2/3. The 2/3 depends upon spatial dimensionality and not much else. I mean, all the problems I mentioned all have the same 2/3 power. Okay, so this is quite interesting because in a Fermi liquid, the leading behavior here of the imaginary part when you analytically continue to real frequencies is omega squared. So this is much larger at low frequencies. In fact, this term is much larger than the I omega term. And that tells you that there are no quasi-particles. It doesn't tell you the Fermi surface disappears. The Fermi surface is still the point where E of K changes sign. That's still very sharp, but the excitations near the Fermi surface are very broad in energy. So there's no long-lived quasi-particle excitations. Right, okay. All right, so we've got an example of a system without quasi-particle excitation, which is metallic. So that's progress. But one very important property of this, pointed out many years later by Seung-Sik Lee, is that this calculation is not systematic. I'm not saying it's correct, incorrect. I think it is correct, but it's not systematic. There's no small parameter here. If you try to introduce a small parameter where you take n flavors of fermions, that leads to a problem because this B coefficient here goes as 1/n. So that's in the denominator. And so if you look at some higher loop diagrams, you might worry that 1/n in the denominator is going to give you some extra power of n, and that simply counting graphs doesn't get right. And that indeed what happens, as Seung-Sik showed in an important paper. So that's, this might or might not bother you. The result is believed to be correct. There's also numerical works and so on that show results like this. But I think it's very important, as you'll see, to really get a systematic parameter when you start thinking about more subtle properties like transport. Okay, so here's my one black hole slide. So how do we address this? Could we address this holographically? So holographically, what do? You take some, in this case, a conformal field theory, ABJM conformal field theory in 2+1 dimensions, and then you turn on a chemical potential. So ABJM is dual to ADS4. When you turn on a chemical potential, you get a charged black hole, a Reisner-Nordstrom black hole. which in the low energy limit is ADS2 cross R2. And so the very low energy excitations here are presumably really important for the properties of this system, which at least perturbatively has a Fermi surface. The trouble is we have no access to those fermion correlation functions. Those are quarks carrying gauge charges. And so there's no direct access to a gauge invariant function that will give you a Fermi surface. I mean, there is a Fermi surface in some gauge invariant quantities involving density correlation functions, say, but those, at least at large n, don't give you any Fermi surface. I think you have to put in monopole effects involving quantization of charge to actually see a Fermi surface. So no one's ever seen the Fermi surface of this system, although I strongly believe there is one here. What people have done instead is add extra matter. They take some gauge invariant matter, which is a meson or a baryon in the Yang-Mills theory, which carries this global U1 charge, and look at its correlation function. So this was the important paper of Hong Liu and others. And what they found was this Green's function of this probe fermion. So this E of k has nothing to do with the actual Fermi surface that's presumably present here, which no one has seen. But it's some other Fermi surface having to do with a chemical potential that's acting on the probe fermion. Anyway, so you take this probe fermion and look at it, and indeed it has, essentially the same form as the result of Patrick Lee, except this exponent is a function of k, and this singular part is coming from this probe fermion interacting with the ADS2 excitations. It was by looking at this that I realized that these ADS2 excitations were connected to the SYK model. So it's sort of like a fermion scattering off a SYK model, sort of in a Kondo model. Okay. Anyway, so this is a function of k, which is it's not 2/3, and of course at the Fermi surface you get any exponent you want. These are smooth functions, but anyway, it's an encouraging sign that this kind of theory has very similar properties, at least for probe fermions, as you get from a perturbative treatment. All right. Okay, so that's all great. Now we have a non-Fermi liquid. Can it explain the linear T resistivity? So here's a very simple fact. It can't. Well, despite that, there were a lot of claims that it can. And for good reason. I mean, there's a very subtle point, depending how you look at it. So what you want to do, in the perturbative theory, is compute the transport scattering time. And there's some general arguments that can also be seen from a Boltzmann equation. There's a single particle scattering time, which would go as t to the 2/3 times this factor here, which accounts for the fact that if you do forward scattering, that doesn't change the current. So backward scattering is maximally effective. So this angle is small because you're scattering of long wavelength gauge fluctuations. So when you account for that, you go from t to the 2/3 to t to the 4/3. So that's the prediction of this theory generically, that there's a transport time that goes to the t to the 4/3. And that's not quite linear, but okay, well, maybe that's getting closer to linear anyway. The holographic theory, there's no difference between these two, because the scattering of ADS2 is actually angle independent. It doesn't depend, all angles are equally likely. And so there's no spatial structure in ADS2. So that cos theta is 0, and so you get the same time. So for the holographic theory, you would say that the distance is just t to the sigma of k, whatever that sigma of k was at the Fermi level. Okay, but this argument is wrong. And that's simply due to conservation of momentum. Now you might think, well, how can anybody overlook conservation of momentum? Well, there's another famous problem where overlooking conservation of momentum was actually the right thing to do. And that's the electron phonon problem. There was a famous paper by Bloch who computed electron phonon scattering in exactly this way. And he got some law which agreed with experiments. Unfortunately, Bloch's theory is actually wrong, strictly speaking. And this was pointed out by Peierls in a paper that's only in German, but anyway. And part of this point was, yes, an electron scatters over a phonon, but eventually the momentum carried by the phonon will come back to the electron. Another way to think of it, when you set up a current flow, it has some momentum. The momentum is conserved. So at long times, the electrical current will be the current that maximizes the entropy subject to the constraint of a non-zero momentum, because the momentum is a conserved quantity. It's not going to change. And that current will be non-zero. So there's always a current will flow forever. And there'll be some decay at short times because the current is not conserved. The momentum is conserved. So there's always, the resistance is actually zero. So this is kind of obvious when you take a holographic hydrodynamic point of view, but it was highly non-obvious from a condensed matter point of view because it was not an effect that was seen before. And the reason it wasn't seen before, when in electron phonon scattering, the phonons will lose their momentum to some impurity. And that happens fairly rapidly. So if an electron scatters over a phonon, you're never going to see that phonon again. The momentum may as well be gone. But in this system, the coupling is infinitely strong. It's so strong that there aren't even any quasi-particles. There's fundamentally, the electron doesn't even exist. There's no distinction between the electron and the phonon. There's just some strongly interacting system. So you can't ignore momentum conservation. Anyway, so that's the key issue, which has kind of been in front of us and why the strange metal problem is so difficult. The resistivity is the most difficult thing to compute, but the easiest thing to measure. So, so it's very hard to explain that, although this theory could explain many other things in principle. All right, so what we need, there are two problems then I pointed out. One is just even for the self-energy, we need something systematic. Systematic large N theory of the Fermi surface without quasi-particles. So this seems like an ideal, maybe some theorists care about it, we care about it. But it turns out, fortunately, if you solve this problem, as I'll argue, we also have some new ideas on how to solve the second problem. So this is the real problem. What is the resistivity of a strange metal or something without quasi-particles when there's some generic mechanism for relaxation of momentum? Okay, so first I'll talk about, I'm almost out of time. That's fine. The systematic approach. And so that we did last year. And once we had that, then suddenly we were able to make some progress on the second more important problem. So how do you make it systematic? Well, here's where SYK-like ideas come in. So you do it, what you did in SYK, you just make everything, put an index on everything, and make your Yukawa coupling. Oh, I'm missing a slide here, am I? No. Okay. You make a Yukawa coupling a random function of these indices, just like in SYK. However, this is not a function of position. It's only a function of these indices in flavor space. So momentum is still conserved. This theory conserves momentum. It's not going to solve the second problem, but it does solve the first problem. And here the idea is that there's some RG flow in this large space of couplings, GIJL, and that RG flow takes you to a universal fixed point. And it's the same fixed point for a very large space of couplings. And you're only interested in infrared properties. So you may as well average over all possible some large set of initial couplings, and hopefully that'll give you a theory under control. And indeed it does. So you can just use techniques that all of you are very familiar with. You can write down a G sigma d pi theory. So G is the Green's function of the fermion, D is the Green's function of the boson, and you get a SYK-like action. Now this is an action over space-time, not just time. And anyway, you take the saddle point of this action, and you get these equations. These are similar to the equation that Patrick Lee used, except everything is fully self-consistent now, and there's no factor of 1 over n anywhere. The n is in front of the action. So these equations are much more complicated than the SYK equations, But fortunately, actually, you can solve them essentially exactly. So in SYK, you get a square root of omega. Here you do get exactly the 2/3. And the basic result is exactly the same that's been known for 20 years. But now it's systematic, and in principle, now you have the door open to looking at corrections, 1/n fluctuations. We've done a little bit of that. That's much harder than the SYK model. There's no time reparameterization soft mode here, but there are, other there's conserved momentum, and we do have to worry about it. But this is a good sign that this works, and further evidence that this result is correct. It will have 1/n correction, this exponent, and in fact, there will be momentum dependence at next order, but no one's ever computed those. But the graphs are there. If anybody wants to take up the challenge, it can be done. It will require a big computer.
Does the theory have a scaling symmetry?
Sorry?
You said there is no reparameterization symmetry.
Yeah, there is a scaling symmetry. Yes, there is a scaling symmetry. In this patch limit, when you take the patch theory, okay, I don't have time to go into that. Yeah. So one of the things we looked at recently with my student Maria Tikhanovskaya, we looked at the OTOC in this theory. And again, now there's a large expansion. There's no uncertainty about what graphs you have to sum. They're very similar to the SYK type graphs, except everything has a momentum label too. And here we found that these very important results of Yingfei Gu and Alexei Kitev, I think Yingfei may talk about something related in his talk later, that in fact at long enough distances, because of this propagator of the scramblon, which has this cosine lambda over 4t factor. So this has a pole contribution which dominates over the branch cut contribution that's present in SYK. And when you account for this pole contribution, you in fact get a maximal Lyapunov exponent. Now this is in the n equals infinity theory, where the self-energy, these self-energies are only functions of frequency. Again, an interesting open question is what happens at order 1/n? Do you move away from this maximal chaos? We don't know. Okay, maybe Yingfei has some thoughts. Okay, so now the second open problem, let me tell you our recent solution for it. Well, proposed solution, let me say, in the presence of momentum relaxation. Okay, so we started with this theory, which has sigma is just a delta function, a function of frequency. It just reproduces well-known results, and as I showed you, gives you a systematic way to address various things, including the OTOC. All right, so now you got to relax the momentum. So what are we going to add? Well, the simplest thing you could add to this theory is just some random potential for the fermions. So this is a basic ingredient in the entire theory of disordered metals. Once you put this in the Coulomb interactions, you can explain a million experiments. It's also what goes into localization theory. But here, we don't expect any localization because the quasi-particles don't exist to begin with. So there's nothing to localize. But anyway, so you put in a random potential. And now you make this also random in space. So now notice there's an R here, unlike here. And then you make the indices run over the same set of values. And now you take an average of V and an average of G, like here. The average of V has a delta function in R. This is why it's going to now relax momentum. And the conductivity is no longer going to be just a delta function. So again, as you return the same crank, you get the G sigma d pi theory. There's one extra term in it from this V squared. And then you compute the conductivity. Before I get there, sorry. You compute the self-energy by solving the saddle point equations. And you find because of the potential, this has a strong effect. It changes the boson propagator to this diffusive form. This gamma is proportional to the impurity density. And the fermion self-energy has two terms. There's the usual elastic scattering term that you get in any disordered metal. This will give you a residual resistivity. But you get, very excitingly, an omega log omega term. So an omega log omega, when you take the imaginary part, will give you something linear in omega and in the dissipated part. So that could be linear in T. Okay, so this term does give you a T log T specific heat that's seen in essentially all strange metals. And this is what's called the marginal Fermi liquid behavior. Okay, so that got us excited last year. We thought we want to do something, but no, in fact, that doesn't work for the transport. So here, you turn the crank, you have a large N method, you have to now compute, instead of solving the Boltzmann equation, you have to compute the conductivity. And the graphs are rather similar to the graphs you get for this OTOC, except the propagators are retarded in advance and so on. So you have to solve these this set of integral equations, which these people have worked very hard on. And what you find in the end is that even though there is a rather singular term, the electron self-energy, just like in the pure problem, this doesn't contribute a singular term to the transport, this thing that involves both interactions and randomness. It's proportional to G squared, so it involves the interactions, and the V is just the potential scattering. So it doesn't do it. And the reason is, again, it is still a fact that all the scattering is forward from this, as far as the interaction is concerned. There's backward scattering from V, that gives you this very, that'll give you a temperature independent resistivity. But once you include interactions, so there's mostly forward scattering, it doesn't give you any singular dependence to the resistivity, and the resistivity be just like in a Fermi liquid. Okay, so that's kind of where we were last year, and we were about ready to give up on all this. And then we had an idea, okay, let's add another term. And the term we're going to add is just like the interaction term, but it's now random in space, the G prime term. So again, you have to include interactions that are random, also like the SYK model. So this will be a correction to that, but now this has the feature that it doesn't conserve momentum. So you have one more term, which is G prime squared. Now you get a delta function, the correlator of G prime. And now it turns out you're in business. So now you can solve the same set of graphs. You get a very similar boson propagator, which is diffusive. And you get the fermion self-energy has this omega log omega term also, just like this random potential gave you. Oh, one more thing I forgot to mention. I mean, once you have these two terms, such a term will be generated at some order in your perturbation theory. But in the large N limit, you want to put this in explicitly because it doesn't get generated in the large N limit. Okay, I'm almost done. All right, so now you've got this marginal Fermi liquid self-energy from the G prime term. And now our hopes actually work out. This singular term, the self-energy, because this involves random interactions, so it's not just forward scattering, gives you a singular term in the transport, and you indeed get a linear resistivity. So that's the basic result. You get a resistivity that has two contributions. There's a random potential term that gives you the resistivity at zero temperature. And then there's a random interaction term that gives you the linear T resistivity. That's exactly what comes out. So that's the basic lesson, that if you have a strongly interacting systems and there is some spatial randomness in your interactions, that can be a very robust mechanism for linear T resistivity in 2 dimensions. Yes?
Why can't you just set V equals to 0?
You can, but then the resistivity will go to 0 at 0 temperature. You can set it to 0. So yeah, so there's we solve a large N equation for arbitrary values of V, G prime, and G. Of course, to solve them all, you have to do numerics, which is still in progress. So there's various limiting regimes where you can see what things look like, and that's what I'm showing here. Yeah, so but one very nice thing about this result, well, okay, is that the residual resistivity and the linear T resistivity are coming from very different sources. And experimentally, that's that's hopeful, because in experiments, these two seem to be quite independent of each other. The degree of disorder and the magnitude of the residual resistivity doesn't seem to determine the slope very much. Anyway, so that's been an argument. Well, maybe the slope of the resistivity is due to interactions only, and the disorder determines the residual resistivity. That's correct, except the interactions also have to be random. Otherwise, you don't get anything. That would be the G prime equals 0 limit, where you do not get linear resistivity. Anyway, okay, so the summary is that at least we have a control theory for the two-dimensional Fermi surface coupled to the critical boson, and the key idea is to make the couplings random in flavor space. So this gives you a theory without quasi-particles. Here there's no randomness in position space, and maximal chaos. But if you make the interactions random, which generically should be there, you in fact do get, this is not something we tune, you get exactly linear resistivity. Okay, thank you. And of course, an important open question is, what's the holographic dual of all this? But even without spatial randomness, without spatial randomness, there's maximum Lyapunov exponent. But does that mean there's a simple gravity description? I'm not sure. Yeah.
All right, are there any further questions for us?
Just a quick question. So again, your random coupling only has this spatial dependence, and indeed has this local variance. This is the delta function. What would happen if you would also include time dependence? At least meaning, right? So because this looks a little bit like the Brownian kind of thing.
Yeah, no, this is a perfectly unitary quantum system.
Quantum system.
So yeah, we haven't thought about that. That will lead to all kinds of non-equilibrium phenomena. Yeah, certainly there's things we can look at.
But the thing is that the coupling, what it means is that it's sort of frozen at a given.
In
time, but indeed it's very.
Everything is in time independent, and in principle self-averaging. I mean, we're doing averaging, but I would expect a given sample to be essentially, it's unlike unlike localization phenomena, where things are not self-averaging, where things localize where there's random impurities. Here, there's no localization because the quasi-particles are broken down, and we just there isn't even an electron, so there's nothing to localize, and as far as we know. It's a quantum chaotic fluid, which provided you give it a mechanism to relax momentum the right way, it will give you linear resistivity. Yeah.
So some time ago, some people considered the relativistic theory with the similar coupling. Right?
Yeah, sure. So the first coupling, the top line, yes, there's many papers. I cited some of those here. Maybe I didn't get them all of them. In fact,
they found that the chaos exponent was not maximal. Is that? That's wrong, or maybe that is
so I think there's a paper by the Ehud Altman and others in Berkeley on the direct fermions with the random coupling of this type, Grosnoval model with a random coupling like this. In 1+1 dimension, they do get maximal chaos. In 2+1 dimensions, they didn't actually solve the equation. They had some numerical results. But I think if they apply the mechanism of Gu and Katev, and we looked at more carefully, which they didn't, I think they will also find maximal chaos.
I have a comment about it. So I think this is not maximal chaos if you go in the time direction,
right?
But if you go close to the butterfly velocity, so you go both space and time, that's where you get maximal chaos. So
yes.
that's
okay.
Just
Thank you.
Okay.
It's not quite like that. Yeah, I think Yingfei can speak. You're the expert.
They observe this maximal chaos only on normal butterfly velocity.
Yes, see.
What happens if you take these materials and experiments and make them dirtier.
Yeah, those have been done.
And what does the strength of the linear T resistivity change?
No, but the residual resistivity goes up.
So now, say making the system dirty doesn't change the random multi-fermion interaction? Is that-
That's what we would have to say, yes. I mean, that's the interesting question that we need to answer. Why is it that when they do radiation damage on these materials, only the residual resistivity changes, but the slope doesn't? So for that, we'll have to have a better understanding of what generates G prime. Yeah, so that's, we're still thinking about that, yeah.
All right, if there are no further questions, let's thank Sabir again.